an exam practice question, which happens to be the last semester exam material with a solution. Our meter one exam, we follow that trend. So I need you to get yourself familiar with the meter one practice question. Is there anyone who have not seen the meter one practice question that I uploaded? Is there anyone? You've all seen that, right? Okay. Okay, so today we actually gonna go over to materials. Let me first start by saying that the purpose of our meeting today is to discuss about the use of analysis of variance when we are comparing more than two groups. Not only that, I'm also going to walk you through assumptions underlying the use of analysis of variance model. Then I'm also going to walk you through how to use a linear regression approach for analysis of variance model. But before we first start, whatever we start, if you really want to investigate in statistics, we're basically going to start with model, statistical model. Now, equation one is an Anova model. This equation one can be in two versions. For instance, if you take a look at this, plus this, you're going to see that the mu here doesn't have a subscript, right? Now, here, this is an error model. We call this an error model. So here, there is nothing. I'm only, here it's just like the response variable can only be explained by the error and the overall mean. There's nothing like a factor. But if you take a look at what I show you on the board, where we have mu I, there's a difference between this guy and this guy. You see mu I, right? The mu I now, then it means we put it into consideration sub means, like the mean of each group. Okay, so what I'm trying to say, in essence now, what I'm trying to show you now is that mu I. And let me tell you, the mu high here is the mu I is equal to mu plus alpha high. Look at that. When I write this mu high, it means I'm writing mu plus alpha I plus EIJ, which means this guy here is the same as the mu high. Statistics is easy when we actually master notations. Like I said, if I said I want to use it, there's no way I can use it. This is an error model. But here, this has included, we've actually put it into consideration group, mean in each group. And the mu I is the same thing as mu plus the alpha I, where the alpha I is basically going to be the treatment effect. Okay, so and that is why we're going to be focusing on it. Now, let me tell you this. When we say analysis of variance, the analysis of variance actually means, the partitioning. So we can say, Anova. So that means partitioning or splitting of the total sources of variations. The splitting of total sources of variations into various components. That's what we mean by analysis of variance. When I split sources of variations into various components, that's what we mean by Anova. But we want to focus on one way Anova. What do we mean? By one way Anova, it means we are splitting the total sources of variation into between and within. Why is it called one way? One way. We're only focusing on between, because in any statistical model, there's always going to be within. I'm going to say that again. In any statistical model, there's going to be error. In any statistical model, there's going to be this guy. Now, this model now is one way. Why is it one way? Because we are only considering a factor, one factor. That is why it is called one way. If I go more than one factor, it's going to be called, if I go from one factor to two factor, that would be two way. I can also have three ways, four ways, and so on like that. But there's, whether we are considering one way or two way or three way, there's always going to be this guy. Why? Why are we also always going to have this guy? Because model is not the same as reality. That is why we're always going to have this guy. Does that make sense? Now, equation 1 and equation 2, they are the same. They represent one-way analysis of variance model. Okay, if that is taken, what we normally want to do in one-way analysis of variance model is to break down total sources of variation. The total sources of variation around what? Around the response. This guy here, Yij, is the response variable. So we actually want to break the total sources of variation around this guy into variability between groups and the variability within group. But the reason why it is called one way is because of the variability between group. In any statistical model, there's always going to be variability within. The variability within group is the error. That's exactly what you're saying. Now, you're basically going to see the mathematical notation for that is that you actually, we now use, we use, you know, I need you to play with notation because, you know, if you look at that very midterm one, Anova is going to be part of the exam. Look at that. Now, if you see this, is the same thing as that guy. Y dot dot bar is the same thing as this guy. Now, look at what you see on the board, SST. That is total variations. Now, the total variation now, you're basically going to see that if all the data points, each of the data point, I'm going to be subtracting the overall mean. And when I subtract the overall mean, I'm going to square that, I'm going to sum that. That will give me the total variation. Now, this total variation now, we want to break it into two. Breaking it into two, that's exactly what we want to do here. Now, let me tell you this. It's just like I know that the sum of square total is Yij minus Y dot. Okay, now when I square that and I sum, it's going to be this guy. Do you know that I can write, if this is the response, I can write it as Yij minus Y dot. Now, do you know I can also do this? Yij equal Yi dot minus Y I dot mean plus Yi dot mean minus Y dot. Okay, look at this guy. It's more or less like I have, maybe I'm talking about 5 minus 2, and I said 5 minus maybe 5 minus 3 plus 3 minus 2. Is it not the same thing as that? Look at that. 5 minus 2 is the same thing as 5 minus 3 plus 3 minus 2, because this guy will still cancel out. That is exactly what we're doing here. If you take a look at that, we introduce this guy, the solved mean. Then when we introduce the solved mean, then we're going to put a parenthesis on this. We're going to put a parenthesis on this. When you put a parenthesis, you now go in a mathematical way If you want to go in a mathematical way, okay, you know, you have Yij minus Yi dot, you got this guy, right? Then plus Yi dot bar minus the Y bar dot dot. If you take a look at what I have here, this guy is still the same as Yij minus Y bar dot dot. Because you know why? This guy, we cancel this guy. Now, if I now want to sum that now, if I want to sum this now, okay, if I want to sum this guy here and put summation Y, Ij minus Y bar squared, it means I'm actually going to do the same here, okay? If I want to do the same here, you remember in math, if I have A plus B all squared, A plus B all squared is going to be A squared plus B squared plus 2AB. Do you remember this guy from mathematics? Then it's going to be this guy squared, then 2 multiplied by that. That is why you see this. When I apply this summation, the entity here is going to become 0. I'm only going to have this guy, and finally, we're going to have that. What is that? It means we have succeeded in splitting the total sources of variation into two components. Okay, this is going to be within, and this is going to be between. Within is like, this is sum of square error, and this is sum of square between, or we call it sum of square treatment. That's exactly what we've done. That is what analysis of variance does. Okay, now, the moment we have that, we need the mean square. You know, when you have the sum of square, like this guy now, SSG, that is the sum of square between, variation between the groups, right? That is what this guy is talking about. Then I need to divide it by the degree of freedom, okay? The degree of freedom for groups, if G represent number of groups, if G represent the numbers of groups, what would be the degree of freedom? That would be G minus 1. Then if I want to get a mean square for group now, I'm actually going to divide this guy by G minus 1. That's what you're seeing. And of course, don't forget, I goes from 1 to G. When G equal to 3, I will go from 1 to 3. Okay, take a look at that formula now. Now, we're going to do the same from sum of square error. Okay, now we also need to divide this by the degree of freedom. Now, if you divide this by the degree of freedom for error, we're going to have the mean square error. Now, divided it by the degree of freedom for error is just going to be this guy. The totality is this guy here is the total number of observations when you pull all the group together. So which means this guy here is going to be, how many do I have in group 1 plus how many do I have in group 2 plus how many do I have in group 3 if you have 3 groups. And that's exactly what you are saying here. This is a N1 plus N2 up to NG depending on the numbers of groups that you have. The moment you have that, okay, so this is the degree of freedom. The degree of freedom for total is going to be N minus 1. The degree of freedom for group is going to be G minus 1. The degree of freedom for error is going to be N minus G. Now, the moment we do that, then the F test, because in analysis of variance, we use F test. Don't forget, when you are comparing two means, when the normal assumption hold, you normally use like T test, Z test, but in analysis of variance, where you are comparing more than 2 groups, we normally use F test. And what is F test? The F test is just the ratio of between divided by within, which is the average between group variability divided by the average within group variability. So which means in analysis of variance, we're actually comparing, we're analyzing the variation within and the variation between, then we find the ratio of that. That's what we always do. I remember when I was in college, when my professor, when I had analysis of variance, and I realized that we were working on variance. I mean, we're comparing means and we call it analysis of variance. I remember when I was in college, I asked my professor, why not calling it analysis of means? Why do we call it analysis of variance? Can somebody answer that question for extra credit? What are we comparing? We're comparing means, right? Why not calling it analysis of means? Why do we call it analysis of variance, even though we're not comparing variance? Can somebody tell me for extra credit? Why do we call it analysis of variance when we're actually comparing means? We're not comparing variance. Can somebody answer that question? Do you all understand my question, right? You know, what are we comparing? Means, right? We're supposed to call it analysis of means, but we are calling it analysis of variance. Why? Can somebody answer that question for extra credits? Go ahead. Means of variability. Oh, so what you're trying to say is that if there is no variability in the first place, I don't need mean. Is that what you're telling me? Extra credits. Look at me. Good job. Because if there is no variation, we don't need mean. So if I want to compare whether this particular guy, if this guy is working for me in my company, and I want to compare this guy with this guy, I want to compare their performances. You know what I'm going to do? I will analyze their variations because I know they are not perfect. Good job. Okay, now when you want to use F test, we need F distribution. You remember when we were using T test, we need T distribution. The distribution is basically going to be the probability, you know, when the null hypothesis is true. When I'm using F test, then if I want to figure out my p-value, then I'm actually going to use F distribution. Does that make sense? So the F distribution now, this is the origin. The F distribution is the ratio of two independent chi-square. Has anybody heard about chi-square distribution? A chi-square distribution has, if a chi-square distribution, if x, look at that, if x follow chi-square distribution with a degree of freedom v1 and y follow chi-square distribution with a degree of freedom v2, then the ratio of x divided by y will follow F distribution. How many degree of freedom are we going to have now? We're going to have v1, v2. Here we're just trying to tell you. Because why am I revealing this to you? Because if you want to figure out a p-value, if you conduct an F test, you need to be able to get a p-value associated with the F test. And if you don't know the probability distribution of your test, of the when the null hypothesis is true, there's no way you're going to do that. And we're trying to tell you now, the F distribution is a ratio of two independent chi-square. This is the shape of F distribution. Is skewed. You're actually going to have different shapes where you have two different combination of degree of freedom. So there are two parameters in a F distribution: the degree of freedom 1, the degree of freedom 2. That's what you see here. Okay, it's right skew. I said that. And number 4, if you take a look at number 4, if I want to get our p value associated with my F test, I'm actually going to, I need the degree of freedom 1, degree of freedom 2. I need to specify that for me to be able to get that. Okay, which means under the null hypothesis, the degree of freedom. Now, I mentioned V1, V2. F distribution need to have two different degree of freedom. Okay, when I'm talking about analysis of variance, when we analyze of variance now, the first degree of freedom will be the degree of freedom for the group. What is the degree of freedom for group? That will be G minus 1. If I have 3 groups, that will be 3 minus 1. That's why you see G minus 1 here. Then the next one will be the degree of freedom for error, which is M minus G. It should not be other way around. If you want to, it shouldn't be this one first followed by that. No, it has to be the way it is. the degree of freedom for between, followed by the degree of freedom for error. That's what you're going to see. And we are doing it on the assumption that the groups we are comparing, the groups that you're comparing, you choose sample in that group from a normal population. Not only that, they must have equal variances. That's an assumption. Even though we're comparing means, we have an assumption that the variances should be equal, and that is what we call homoscedasticity. Homo means constant variance, across group. But let me tell you this can be violated. The moment there's a violation, we have a way to investigate whether that assumption holds. Otherwise, we actually need to do something. We need to use a different approach. Okay, if an outlier is present, right, this assumption may not hold. Okay, we have other assumptions that may actually undermine the performance of a model. Okay, let me tell you what I work on my PhD in 26 that I defended in 2016. Initially, I defended my PhD work at the University of University of Oxford in the United Kingdom, all the way from Nigeria. You know what I did in my PhD? When there's a violation of assumption for analysis of variance, what is the way out? I don't want to use non-parametric. I don't want to use randomization tests, but I still want to use parametric approach. And that was what I did. I have to revisit this distribution that I just showed you now. I revisited this distribution. I reparameterize that to be able to use F-test. I didn't call it F-test anymore. I call it exponentiated F-test. So there's always going to be a way out. Okay, now take a look at this. Which means if I want to, this is the F-test and it follow F distribution with that. That's what we're trying to say. And we can get the p-value associated with that, putting into consideration degree of freedom for groups and the degree of freedom for error. And don't forget, the p-value is just what is the probability of observing an extreme value when the null hypothesis is true. That is why, that's why the p-value is going to be around here. The probability of observing an extreme value when the null hypothesis is true. Now, when you want to answer a question that has to do with the analysis of variance, we normally consider a table. This is the way in the table. Look at the first column. The first column is going to be source. What does it mean? Source of variation. Don't forget, I told you. Analysis of variance is the splitting or the partitioning of the sources of variation into various components. What do you see? You partition the source of variation into variation between groups. Variation between groups is what is representing groups here. Error is the variation within. So this is between, within. And this guy here is the total variation. And what do you have in the next column? Of course, degree of freedom. The G minus 1, the degree of freedom for group. The N minus G, degree of freedom for error. N minus 1, the degree of freedom for total. Some of you, you've seen different degree of freedom before. You'll be wondering, what does it mean? At times you're going to see divided by minus 1, divided by minus 2, divided by M. So what is the difference between that? See, when I'm talking about total, the degree of freedom is always going to be M minus 1. I'm talking about total observations. The degree of freedom is going to be M minus 1. If I'm talking about groups, the degree of freedom will be numbers of groups that I'm comparing minus 1. If I now want to get the degree of freedom for error, will be different between the total observation and the numbers of groups. Do you know the next column is sum of square? This is going to be sum of square between, sum of square within, sum of square total. And If I want to get the mean square, it's basically if I want to get this guy now, is this divided by that? If I want to get this guy, this divided by that, then we're going to have these two. We don't get mean square for total. There's nothing like mean square for total. We're not interested. We're really interested in mean square for error and mean square for between. And you know what? If I want to get my F now, the F statistic now is going to be this guy divided by that guy. Then the only thing I'm going to do is to get the p-value associated with that. Now let's go to the data now. In the data, the other time we're working on sandwiches, the example we started with, how many hands can 3 different sandwiches attract? And don't forget, you replicate, right? You replicate for each group, for each sandwiches 8 times. The total number of your observation is 24. Don't forget. Now, in this question, they wanted to state assumption, state HO and HA, calculate the test statistic, given the SST, the sum of square total is that. Okay, calculate the p-value, then make a decision. Now we have a way to do this in R. This is a way to do that in R. One, you just write AOV. AOV means analysis of variance. AOV response. This is going to be response variable on the filling here is basically going to be the explanatory, the factor. Don't forget, this is categorical. Then you automatically, when you put the summary, you're automatically going to see this result. Oh, what is this? What does 2 represent? Oh, that is the degree of freedom for 3 groups. 3 groups, that will be 3 minus 1. Then the degree of freedom here, 21. The residual is like n minus g. Then now you have your p-value here. Arrow has automatically generated that. Now when you have a p-value there, you just need to compare with the level of significance. Okay, if the level of significance is 0.05, then compare this p-value 0.011 is less than 0.05, then you're basically going to reject the non-hypothesis. Rejecting the non-hypothesis, you are trying to tell the world different exists among the means. It means sandwiches, okay, they don't attract the same number of hands. That's what it means. Sandwiches don't attract the same numbers of hands. It means some majority of the hands, some hands would like to go to a particular sandwich. That's what it means. Because the p-value is less than 0.05. You're rejecting the non-hypothesis. And rejecting the non-hypothesis, you are trying to tell the world that even though different exists, this very difference, it is not the one that can be attributed to chance. This is a real difference. There's a big deal here. Any question on that? Any question? Okay, now the next one we want to talk about is Anova for regression. Give me 1 second. I'm actually going to. I got some people online. Let me tell you this. If you want to attend my lecture online, you need to send me a message, okay? So